So, if you're reading an ebook today, there is a very, very good chance that the spaces between the words are actually lying to you.
Oh, yeah. Completely.
Right, because every comma, every quote, every number you look at on that screen, it is governed by this invisible microscopic grid.
A grid that we completely take for granted.
Exactly. And, if you happen to mix English and Chinese on that same grid, the entire illusion of a clean, readable page just completely shatters.
It's true. The layout engine trying to render that text basically just panics. I mean, we are so used to thinking of digital space as this infinite accommodating blank canvas.
Like a piece of paper?
Right, like a blank piece of paper.
Yeah.
But we forget that it is actually a really rigid mathematical structure.
Yeah.
And when you violate the rules of that structure by, mixing different writing systems, you get this massive typographical culture clash.
Which is exactly the mission of our deep dive today. We're going to look at what actually happens when two totally different linguistic systems collide right there on your screen, and how one programmer is using Haskell code to basically force them to play nice together.
It's such a fascinating workaround.
It really is. So we are drawing from a blog post that was published on June 27, 2026 by a developer named Ang. And this is actually, get this, part 172 of their ongoing Notes on Haskell Programming series.
Which is just, part 172 represents an incredible level of dedication to a single project.
Yeah, that's not a weekend hobby.
No, not at all. Ang is building a tool called TXT2Book, which essentially converts raw plain text into beautifully formatted digital books. And this specific problem Ang is tackling in this post is, well, it's really a hidden art form. Digital typography.
Okay, let's unpack this, because we need to move from the broad idea of a digital canvas to the highly specific visual problem that Ang is trying to solve here. I'm trying to picture this invisible grid you mentioned earlier. Like, if we have a screen full of Chinese characters, how is the computer actually mapping that space out?
Well, to understand the grid, we have to look at the fundamental conflict between CJK characters.
And CJK, that stands for Chinese, Japanese, and Korean, right?
Yes, exactly. So the conflict is between CJK characters and standard ASCII text.
And ASCII is just our standard English letters, numbers, common punctuation.
Right. So CJK characters are what typographers call full width or double width. You have to think of them as existing on a perfect, uniform grid where every single character occupies a perfect square.
Okay, so like a tile.
Yeah, exactly like a tile. They all take up the exact same amount of horizontal space, no matter how complex the actual drawn character is.
So they have a very symmetrical, totally predictable footprint.
Precisely. But ASCII characters, the alphabet we use in English, those are half-width. They're naturally narrow. Think about it. A lowercase I takes up far less horizontal space than a capital W.
Oh, sure. They're fluid.
They're fluid. So if you have a grid that's built for perfect squares, and you suddenly drop a narrow, fluid letter right into the middle of it,
the layout engine must completely lose its mind trying to calculate where the next line should even start.
It does. It creates total chaos for the paragraph wrapping. Software calculates where to break a line of text based on those predictable widths.
Right.
So when you mix those narrow ASCII characters into a solid block of full-width CJK text, the math for the end-of-line justification just breaks. It leaves you with these ragged edges, orphaned characters, and just incredibly awkward spacing right in the middle of a sentence.
It's like building a brick wall where every brick is perfectly uniform, right? Like a standard cinder block.
Okay, yeah.
But suddenly, someone hands you a handful of tiny Lego pieces and tells you to, incorporate them into the middle of the wall. The structural integrity, or in this case, the paragraph wrapping it, just falls apart. You can't shove a tiny Lego between two massive cinder blocks and expect the wall to stay straight.
That visual perfectly captures what the layout engine is struggling with. And Ang gives us a really stark example of this using just basic punctuation.
Punctuation, really?
Yeah. To a Western reader, a standard colon and a standard quotation mark. They seem perfectly normal. But Ang shows a sentence in Chinese text that contains a piece of dialogue.
Okay.
And in the raw code, someone typed the Chinese characters, but they used a standard ASCII colon, a standard ASCII quotation mark, and a standard ASCII comma inside the dialogue.
Oh, I see. So inside that uniform grid of Chinese characters, those tiny ASCII punctuation marks must look disastrous.
They really do.
Because they're too skinny. They act exactly like those tiny Lego pieces, just completely throwing off the visual rhythm of the surrounding cinder blocks.
And Ang's fix for this is fascinatingly literal. Instead of trying to, force the layout engine to accommodate the skinny punctuation, Eng just intercepts the text.
Oh, interesting.
Yeah, the code literally swaps out those ASCII punctuation marks for their full-width, double-width equivalents that are naturally found in CJK typography.
So instead of a tiny little quote mark just sort of hovering in the air, taking up a tiny slice of space, the code swaps in these beautiful, structured, full-width bracket-style quotation marks.
Exactly.
And the skinny little comma gets replaced by a full-width comma that perfectly occupies its own square tile on the grid.
Yep. By forcing those punctuation marks to be fixed with characters, Eng completely restores the visual harmony. The layout engine goes back to dealing with uniform squares, so it just stops making those awkward spacing mistakes.
Okay, punctuation totally makes sense. But where this deep dive gets really wild, I think, is when we look at how this applies to actual letters and numbers.
Oh, yeah. The alphanumeric problem.
Right. Because Aang gives the second specific example in the source notes. It's a sentence that translates to, our GPU got a 95% approval rating, but the words GPU and 95% are written in raw, skinny ASCII text right smack in the middle of the Chinese characters.
Yeah, we call this the alphanumeric grid break. Just like the tiny punctuation, that raw ASCII acts as a massive speed bump in the middle of a smooth road. You have these beautiful wide Chinese characters, and then suddenly GPU is all squished together.
So the primary fix here follows the same logic, right?
It does.
The code spots the standard letters and numbers and just swaps them for their double width equivalents. So a standard GP and U are replaced by this wide, spacious, full width GPU and a wide 95% sign.
Yes.
And then they take up the exact same horizontal real estate as the Chinese characters. The wall is made of uniform bricks again.
That is the primary solution, yes. But what's fascinating here is that Aang actually presents an alternative method for dealing with these letters and numbers.
Oh, what kind of alternative?
Well, instead of actively converting the character itself to a completely different full-width Unicode character, Aang suggests you could just inject an extra half-width space character next to the existing single-width character.
Wait, let me make sure I have this right. So instead of going into a database and finding a special YG, the code just prints a standard G and then hits the spacebar.
Pretty much, yeah.
Then a standard P, spacebar, U, spacebar.
Exactly. Because mathematically, a half-width character plus a half-width space equals one full-width square. It perfectly simulates a double-width footprint on the grid.
Okay, I am going to push back on Aang's final choice here.
Okay, let's hear it.
Think about this from a purely programmatic standpoint. Writing a script to inject a space after every ASCII letter is basically what, a one-line loop?
Yeah, it's very straightforward.
It is infinitely simpler than building some giant lookup table to map and replace every single character type on the keyboard with a special full-width version. Why wouldn't Aang just use that spacing method across the board? Just take the shortcut.
I love that you brought this up because this is where coding stops being about pure math and really starts becoming a subjective art form.
Really, an art form?
Yeah. Aang actually notes in the post that they are still contemplating whether to pursue this spacing approach. And the hesitation isn't about whether the code compiles. It's about the aesthetic.
The aesthetic. But, I mean, the computer doesn't care about the vibe?
But the computer doesn't, sure, but the reader does.
Yeah.
Aang points out that adding those extra spaces makes the overall layout look, quote, thinner and spacious.
Thinner and spacious. Let me process that.
Think about the actual weight of the ink on the page.
Okay.
A true full-width G is drawn by a typographer to explicitly occupy a large square. The lines of the letter are naturally thicker. It has a certain visual gravity to it.
Right, it fills the space naturally.
Exactly. But a standard skinny G with a blank space next to it, yes, it occupies a square of space mathematically, but visually, half of that square is just empty air.
Oh.
So it looks hollow compared to the dense Chinese characters surrounding it.
Oh, wow. I completely missed that. So even though the math works perfectly for the layout engine, the visual weight is totally off. That proves that Aang isn't just trying to prevent software crashes here. Aang is acting as a digital typesetter, obsessing over how the pixels literally sit on the page.
Which is a beautiful concept, right?
Right.
But it presents a serious engineering problem. We've established Aang is making subjective, artistic choices. But a compiler doesn't understand art or, spacious vibes.
No, it just understands instructions.
Right.
Yeah.
So how do you translate a visual aesthetic into rigid Haskell code to automate this for an entire ebook?
Right, because Aang isn't doing this by hand, sentence by sentence. You'd go crazy. This brings us to the mechanics under the hood.
Let's get into it.
In the source, Ang introduces a specific command created for this program. It's the -- tidy flag. And when a user runs that flag, the program just hunts down all these layout issues and fixes them automatically.
And to build that engine, Ang utilizes a Haskell function called folder and combines that with another function called treplace.
Okay, let's make sure we don't lose anyone in the technical weeds here. Can you explain fold for me?
Sure. Folder stands for fold right. The easiest way to visualize it is to imagine a snowplow moving from the right side of a sentence all the way to the left side.
A snowplow. I like that.
Yeah. And as it moves across the text, it scoops up every single character one by one, checks it against a set of instructions, processes it, and then leaves a perfectly clean, modified trail of text behind it.
Okay, so folder is the snowplow moving across the text.
Yeah.
That makes treplace the actual mechanism doing the work, like a salt spreader on the back of the plow looking for ice and dropping salt.
That's a great extension of the metaphor.
So treplace spots the half-width character and drops in the full-width replacement.
That's the mechanism, yes. But Ang runs into a very specific technical hurdle here in how Haskell requires its data to be packaged.
What kind of hurdle?
Well, treplace is a strict function. It demands two completely separate arguments handed to it independently. Argument A, which is the thing you want to find, and argument B, the thing you want to replace it with.
Okay, seems simple enough.
But the lookup table, Ang built the master dictionary. Of all the characters that need swapping, it doesn't hand out the data separately. It provides the data as a single pair, which programmers call a tuple.
Ah, a tuple. So instead of handing the function, here is A and here is B, the tuple basically says, here is a single sealed package containing both A and B.
Exactly. And treplace doesn't know how to open packages. It just throws an error because it expects two items, not one package.
Here's where it gets really interesting. Zhang solves this elegantly using a Haskell function called uncurry.
Let's hear the analogy for this one.
So treplace is like a two-pronged electrical outlet, but our data is a single three-pronged plug. Uncurry is basically the travel adapter that makes it fit perfectly.
That is exactly what it does. Uncurry acts as a structural adapter between the shape of your data and the shape your function requires. It doesn't actually change the data itself, it just changes how it's delivered to the function.
It's so clean. But, Ang being Ang, we don't just get one solution. The source notes that if a programmer doesn't want to use an adapter like uncurry, there is a workaround.
Yes, the lambda alternative. Ang notes you can bypass uncurry entirely by writing a lambda, which is basically an anonymous function.
Wait, an anonymous function. We went from beautiful visual typography to what sounds like hacking the matrix. Let's slow down. What does a lambda actually look like in the code?
It's surprisingly literal on the screen. Instead of calling the uncurry adapter, you type a \, then a set of parentheses containing the variables for your tuple.
So let's call them S and D for source and destination.
Perfect. So you have your S and D. Then you draw a little arrow and explicitly write out T replace ST GSRS. You're spelling it out for the compiler.
So if uncurry is snapping on a pre-made travel adapter, the lambda is you, the programmer, just taking some wire cutters and hot wiring the plug yourself.
Yes.
You're explicitly writing a tiny temporary set of instructions that says, take this package, break it into S and D, and just shove them into treplace.
That's exactly it. And some programmers heavily prefer the lambda because it is incredibly explicit. When you read the code, you can see the exact mechanics of the data being broken apart.
No hidden magic.
Right. But others prefer uncurry because it's concise and it reads more like natural language once you know what it does. It really just comes down to personal style.
Speaking of personal style, I really want to look at the lookup table itself. Ang's mapping table is called single width to double width. This is the master list where Ang defines that a standard comma becomes a full-width comma, and there is a massive deliberate design choice hidden in this table.
Oh, it reveals everything about how Ang approaches this entire project.
Yeah, because when Ang defines the replacements for the punctuation in the Haskell code, Ang explicitly chose to use literal characters.
Right.
You physically see the beautiful CJK bracket quote typed directly into the source code.
Which is highly, highly unusual for a mapping table like this. Typically, a programmer would use standard Unicode escape sequences.
Meaning what, exactly?
Meaning instead of pasting a visual symbol into the code, they would just type X211C, which is the universally safe machine-readable code for that specific quotation mark.
So what does this all mean for the programmer? If X21C is perfectly accurate and, mathematically safer for a compiler to process, Why go out of your way to copy and paste the actual literal symbol into your raw text file?
Because it allows Ang to, and I'm quoting the source directly here, immediately see the visual mapping.
Ah,
When you open that code file, you don't have to mentally translate a random string of numbers like X21C in your head to remember what shape it makes. You just see the shape.
right there on the screen.
Right. It is a testament to the fact that Ang is fundamentally working on a visual problem. The code isn't just abstract logic. The code is a literal mirror of the typography itself.
The code is the canvas.
Yes, Ang is sculpting the text.
Yes.
And they point out in the post that they've been doing this for, quote, all these moons on the TXT2 book project.
All these moons. I love that phrasing so much. It sounds like this ancient monastic pursuit, just sitting in a digital monastery somewhere, obsessing over the width of a comma.
But it requires that exact level of patience. I mean, handling these quirky little text manipulations, figure out the perfect adapter for a tuple, debating the aesthetic weight of a blank space. Ang admits that wrestling with these layout issues is honestly half the fun of the project.
The source even mentions that Ang used AI to unearth some clues to resolve these Haskell configurations, which I think is a really fascinating detail.
It really is.
Because even when we have access to the most advanced neural networks on the planet to help us write code, the human programmer still has to step in to say, no, the AI's math is right, but the vibe is off. The ink looks too hollow. The human still has to care about the grid.
Exactly. AI can give you the syntax for a tuple in 2 seconds, but it doesn't instinctively understand the typographical culture clash. It takes a human to look at the page and actually feel that something is wrong.
Right. So for you listening, the next time you are reading a beautifully formatted ebook or just a perfectly aligned document on your screen, take a second to look closely at the punctuation.
Notice the details.
Yeah, look at the spacing around the numbers. Because that seamless, invisible reading experience you are enjoying, it only exists because programmers like Ang are behind the scenes writing complex code to obsessively manage those invisible grids.
If we connect this to the bigger picture, I think it reminds us that digital cleanliness is always a manufactured illusion.
Definitely.
It takes an immense amount of hidden labor to make things look effortless.
Absolutely. So to wrap up our deep dive today, I want to leave you with something to ponder on your own. We've seen how standard ASCII text, the fundamental building blocks of digital English, inherently disrupts the visual harmony of CJK languages.
It physically breaks the grid.
Right. So if that's the reality of how these characters render, how much of our fundamental digital infrastructure was built from day one with an exclusive bias toward the Western alphabet?
Wow.
And how much invisible, frustrating work are programmers all over the world constantly doing every single day just to make their native languages fit into a rigid box they didn't design?
This raises such an important question about the assumptions baked right into our technology. It really makes you rethink that invisible grid, doesn't it?
It absolutely does. You look at a screen, you expect a blank piece of paper. But it's always a grid. It's just a matter of who designed it.